a bug located at this point. Yeah. So this location, the current location, right? Yeah. The current location. Then moving along the straight line toward, yeah. So the destination is this point. The destination point. Yeah. At what rate is the bug's temperature changing if the temperature function is given? Yeah. It is a 3-variable function. Yeah. Units are in meters and degrees in Celsius. Yeah. All right. Yeah. Here, to do it, there are several steps. Yeah. So let me give you step by step for the solution. Yeah. All right. First, starting point A, 394. Endpoint B, 573. Right? Then we need to draw a straight line. Okay? Yeah. So then we need to represent when the point moves from A to B at any point in the middle. Yeah. So let's assume the arbitrary point in the middle, X, Y, Z, right? Yeah. Yeah. Now we need to represent, we need to write a parametric equations for this point. Yeah. Parametric equations. Yeah. Yeah. So the first step, step 1, this is step 1. Parametric equations. Yeah. All right. How to write it? Remember in class, I gave you a concept called linear interpolation. Linear interpolation way, in order to represent a point in the line segment between A and B, we should use the linear interpolation expression. How to do it? Yeah. So here we use the parameter t. Okay. Yeah. T is the parameter. Yeah. Moving from A to B. And at the A point, t equals 0. At the B point, t equals 1. So from 0 continuously change to 1. Yeah. So that's the parameter t, the range of the parameter t. Yeah. All right. So in that way, so we can write using the linear interpolation way. Yeah. So the arbitrary point x, y, z. Yeah. Here I like to use the vector way. So x, y, z equals the linear interpolation of A and B. Yeah. A, we use 1 minus t. Yeah. Point A, 394. A point. Why 1 minus t? I will explain to you later. Then t times the B point coordinates, 573. Okay, all right, yeah. Because here you can see, you can verify, in this case, when t equals 0, you take point A. When t equals 1, you take point B. So that's what we like to have, right? From A to B, t changes from 0 through 1. Yeah. So that's the direction to go. Okay, all right, yeah. In this way, so you write a parametric equation, right? Yeah. So your parametric equation looks like, here, x of t, because t parameter. So 3 plus 2t, right? Yeah. Y of t, 9 minus 2t, right? Yeah. Z 4 minus t, right? Yeah. So that's the parametric equation. All right. That's step 1. Step 2, because the goal is the rate of change, right? Yeah. The temperature rate of change. Yeah. At what rate? Yeah. So this t function, the temperature t function, because each x, y, z, each of the variable can be written as a function of t, right? So capital T can be written as a function of t, right? Yeah. So if you replace x by its parametric equation here, replace x by 3 plus 2t, y by 9 minus 2t, z by replaced by 4 minus, so you get a capital T of little t function, right? Yeah. So now to calculate the rate of change, we need to calculate the dt of t over d little t, right? Yeah. Then we know by the chain rule. Yeah. So we learned by the chain rule, it should be partial t over partial x times dx over dt, right? Partial t over partial y times dy over dt. Next, partial t over partial z times dz over dt. Okay, all right. So you can calculate, right? Yeah, so you can calculate. Then, because the current location, look at the current location is here. So that means the current location corresponds to the little t equals 0 point. So when you calculate this rate, you should calculate the rate at the current location, right? T equals 0. Yeah. All right. So that is, you should calculate, this derivative dt at a 0 point. Okay? Yeah. At a 0 point. Yeah. Calculate this one. Yeah. All right. Calculate at this one. So this is step 2. Yeah. Step 2. Yeah. Okay, you're using this chain rule formula. Okay, yeah, you can calculate, so you can find a number. Yeah, some number here. But that's still not a final answer. To get a final answer, you need to do the last step, step 3. Because here, when you move from A to B, because this vector, AB vector, so here, let's look at the AB vector. AB is a vector, right? And the length of AB vector sometimes could be long, sometimes could be short, right? So long, short. So if you stretch longer or shorter, the rate of change will be different. So that is something, the answer could change. But when we calculate rate of change, we should use the, some, let's say, stable way, right? Yeah. So we don't want that. When you stretch longer, shorter, then your rate of change will be different. That's not good, right? Yeah. So in order to eliminate that factor, the length of AB vector, yeah. So there is a, variable length factor. So you want to normalize it. Yeah. So step 3 is the normalization step. So this normalization step, you want to divide it by the length of AB. In that way, yeah, it's a univector, right? Yeah, so it becomes a univector. So whatever the length of AB vector is, you always, at the end, you always divide it by AB vector. Okay? Yeah. So that's why the step 3, last step, you need to divide by the length of AB vector times dt of 0, little dt. In that way, yeah, so the rate of change, you will use, some reasonable scale, right? Yeah, always on unit vector. Yeah. So no matter how long is the length of AB, yeah, you always scale it to a unit vector. Yeah. So that's a, normalized way. Yeah. We call it a normalized way. Yeah. So after you complete these 3 steps, 1, 2, 3, so you find a solution. Okay?